Question 9. This question is about alkenes and polymers. So this is organic chemistry. Ethene, C2H4, can be represented by different types of formula. Complete the table by giving the missing information. So they want you to know molecular formula, empirical formula, general formula, and just to enhance your learning, we're also going to add displayed formula. Because I've seen that on past papers before. So, do we know what all of this is? Let's start with general formula. General formula is like an equation. There's only 2 general formulas that you need to know. So we're revising right now. For general formula, you need to know the general formula for alkane and alkenes. For alkane, it is CnH2n plus 2. And alkenes, it is CnH2n. So since this is an alkene, alkene, the general formula would be CnH2n. And you can check this. It's like algebra. You can actually check. In this case, n is 2. So then what is H? H is 2 times n. So 2 times 2, and that's 4. CnH2n. So when you write that, you can cross-check by yourself, and you know you definitely got it right. Now, that's general. It's the one with the n and the 2n. Molecular formula is the actual number of carbons and hydrogens in this molecule. So there's 2 carbons and 4 hydrogens. Whereas empirical formula is the simplest ratio, right? The simplest ratio of atoms. Whereas molecular formula is like the actual number of atoms. So the simplest ratio is, think about it, let's blow this up a little bit. C2H4, simplest ratio is if I just divide them both by 2, right? Divide both by 2. Therefore, I would get just one C or C1, and then H divided by, H4 divided by 2 would be H2. So that's the simplest ratio, CH2. I cannot make that more simple. And then displayed formula, guys. Displayed formula is literally when you draw it all out. When you just draw it out, it's displayed. And in this case, the display formula for ethene would be like this. Notice that it's an alkene, which is unsaturated hydrocarbon, meaning there is a double bond right there, and you have C2H4. Okay. Part 2. Ethene is a member of the homologous series of alkenes. All members of the same homologous series have the same general formula right here. Give 2 other characteristics of a homologous series. So homologous series means, for example, let me just show you because it's hard to. So if it's ethene, this is number of carbons. Shimmy this over there. So if it's 2 carbons, that's ethene, right? That's ethene. Whereas if it's 3 carbons, that's propene. And then if it's 4 carbons, that's butene. And if you write out their actual equations, ethene is C2H4, propene would be C3H6 because you times the 3 by 2, right? CnH2n, so just times by 2. And then butene would be C4H8, exactly. And can you see how each of these differ? They've gone up by 1 C, and how many H's have gone up by? 2. Isn't it, right? Because from 4 to 6, it's 2 more hydrogens. And what about the next one? Again, the carbons have increased by 1 and the hydrogens have increased by 2. So this actually shows you, so this adds CH2 each time. This is a series, means that it's a pattern. So what the pattern is that each member of the homologous series, these are the members, right? Each member differs by CH2. Now, you don't need to draw it out next time. You just have to memorize it. But I've drawn it to really convince you that they differ by CH2. You can also say that they have the same functional group. They have the same functional group. All members of the homologous series have the same functional group. And you can also say that they have same chemical properties. Means that they do similar chemical reaction, such as combustion. Okay, so remember that this gets asked quite a lot, like, what are the characteristics of a homologous series? So try to memorize these points, and you can get these 2 easy marks on the test. Okay, next part says, ethene is used to make polyethene. State the type of polymerization to form polyethene. And if you've done your revision, you would know that ethenes can do a few different types of reactions. One of them is addition. Because it's got a double bond, it's like a double bond is like, imagine your arms folded up in front of you, like right here. It can open up. If you open up your arms, you can then go on to hold on to something new with each of your hands. And that is the addition reaction of an ethene. It just opens up this double bond, and then it's got 2 hands that have opened up that can go on to grab onto new things as they undergo this addition reaction. And that helps us answer the next question, which is complete the equation for the polymerization of ethene. So here, this is ethene. Ethene is this thing here. And the N just means there's a lot of them. They're not going to draw a lot of ethenes. So they're just going to draw one. N means there's a lot of them. And what would happen to this ethene when it undergoes addition polymerization is that it will open up its arms, and therefore the arms are no longer double. It's just a single bond now. It opens up the arms to hold on to other ethenes next door. And these 4 hydrogens you're seeing on the left-hand side, they're still there. Like, they haven't gone anywhere. And what else is missing in this diagram? Everything in a chemical reaction has to balance, right? So I've got the 2 C's, and I've got the 4 H's. What else is missing? The N. And I have to write that N at the right bottom corner. And this just means that this unit repeats itself. So if I drew another one next door, it means that, there's another ethene next door, which has also opened up its arms to join up with the blue one, and it's got another H. Do you see? It keeps repeating. And since you cannot draw all these repeating units, you just write N there to tell them it's going to be repeating. And this is a polymerization reaction. Okay, part 3. Polyethylene is used to make plastic bags. Cornstarch from plants can also be used to make polymers for plastic bags. The table gives some information about polyethylene and polymers made from cornstarch. And here's the information. So these are 2 different types of materials, and then how much they cost, and their strength, and then the time it takes for them to decompose. And it says, use the information in the table and your knowledge to discuss the advantages and disadvantages of using polyethylene to make plastic bags. So if it's 5 marks, you want to address as many different points as you can. If you just address one point, even if you talk a lot about one point, you will only get 1 point. So many different points. So let's just look at each row of this table. What can we draw from the conclusion? From this row, I would say, what would you say about polyethylene? We're talking about polyethylene, so this guy here, right? So what makes polyethylene an advantage or disadvantage here? The cost is cheaper, right? So that's my first point. It is cheaper. The second row, well, you have to say cheaper than what, right? Cheaper than cornstarch. The second row, what is my take-home message from the second row? What's the strength like? Looks like it is stronger. In fact, you can use data, like really say it's twice as strong as cornstarch. 100 is twice of 50, stronger. And then the third row here, time to decompose. Ooh, that is not good, isn't it? That takes 450 years to decompose. So therefore, the first one is an advantage, another advantage, the third one is a disadvantage because we don't want things to decompose. I mean, we don't want things to take a long time to decompose because it's not good for the environment, isn't it? So so there's lots of points we can take down. We can talk about is cheaper. We can say that is stronger. And these are the advantages, right? The advantages. Let me write this in blue color. So advantages would be cheaper, stronger, and then what are the disadvantages? Disadvantages, looking at the table, is that long time to decompose, and that means it is, which means that it is not non-biodegradable. Non-biodegradable means it does not decompose when you try to get rid of it, and that's not good for the environment. And why is that bad? It is a problem, difficult to dispose because it will just build up in the landfills, right? Just to dispose of, because it would take up lots of landfill space because it does not degrade. The other thing you must know about polyethylene or just plastics is that it's difficult to burn them. Sometimes when we want to get rid of trash or litter, we burn them, but it's not feasible to burn polyethylene because it will produce toxic fumes. So cannot burn to get rid of because produces toxic fume. Okay. Yeah. And another disadvantage is, where does polyethylene come from? Where does it come from? It comes from the combustion or the burning of fossil fuels, right? It comes from fossil fuels basically, because after you separate the fossil fuels by the crude oils, then you can crack it, and when you crack a large hydrocarbon, you get smaller hydrocarbons, and one of the smaller ones is an ethene. So then you can use the ethene to do addition, polymerization, to make it into polyethylene. So the point is, polyethylene comes from fossil fuels, right? From fossil fuels. And what's that bad? What's bad about fossil fuels? It is a non-renewable energy. So this question utilizes a lot of information from the table, which we've talked about, but also your general knowledge of fossil fuels and biodegradability and the environment. All right, next question, C. The diagram shows the repeat unit of another polymer. Draw the displayed formula, display, right? All the things are displayed out, of the monomer used to make this polymer. Draw the displayed formula of the monomer used to make this polymer. So the key point you want to realize is that these arms are stretched out and they're not binding to anything here. What does that remind you of? It should remind you of right here, this bit here. See these arms? They are stretched out and they're supposed to be connected to something next door. So if those arms are stretched out, what does that tell you about originally? It means that it was originally a double bond, because now they've opened up into this single bond in the middle. Understand? So once you understand that, you spot that, you'll realize that it must have come from what? What must have made that? It must have come from a molecule where there was originally a double bond there without these arms open up. So just always think of the arms closed up or open up, closed up or open up. Here they're open up. That means the thing that was used to make them had the original double bond, so the bonds were closed. So I'll color code this for you. These are the two carbons, right? So these are the two blue carbons right here. And now remember, we have the double bond. We actually have it. And since you already have it, then you won't have these opened up green bonds anymore because the arms have closed up. And everything else stays exactly the same. So I've got the two hydrogens at the bottom. And I've got one hydrogen here. And then this connects to another carbon, which connects to another three hydrogens like that. And by the way, guys, this is just 1 mark. So you got to be smart. You got to realize it's not supposed to be a very complicated question. All you had to do was spot that and then put in the double bond. Okay, question 10, it says, this question is about carbon and its compounds. Draw a dot and cross diagram to show the outer shell electrons in a molecule of carbon dioxide. Okay, so dot and cross diagrams, our favorite. Now, I have helped you find carbon, which is here, group 4, so that's this one here. And then also oxygen, which is here, group 6. So I've already plucked those out for you. Now, how do you draw a dot and cross diagram? You have to do it step by step. You first of all think what group they're in. So look at carbon, group 4. So if it's in group 4, what does that mean? It means that how many electrons does it need in order to be stable? How many more does it need? It needs 4 more electrons, right? 4 more electrons. And what about the oxygen? What about the oxygen? It's in group 6, so how many more electrons does it need to make 8? 6 plus 2 is 8, so it needs 2 more electrons. See that? Okay. And then you should also realize the CO2, they've already given you a lot of the clues. So CO2, if you're going to draw this, what would you put in the middle to make it CO2? It would be a C in the middle, right? With the 2 O's next to it. Wouldn't that make more sense, right? So therefore, I'm going to draw my carbon smack in the middle, like this, carbon. And you only need to draw outer shells, yeah? So how many electrons in the outer shell? 4, because group 4, right? 4. So it's going to be 1, 2, 3, and 4. Now, I'm going to draw one of the oxygens first. Let's draw the oxygen on the left-hand side first. The oxygen on the left-hand side, look at this. The oxygen has 6 electrons. It needs 2 more. If you need 2 more electrons, it's a fair game. You also have to share 2 electrons. Therefore, oxygen will be sharing 2 electrons with the carbon. See that? That's how you draw this sharing zone. It's got to be fair. If you need 2 for oxygen, you share 2, and therefore carbon shares 2. They both share 2. That's 4 in there. And then you fill in the rest of the electrons in the oxygen. Make sure you draw the electrons in the sharing zone first. Then you just fill in what's left. So you're supposed to have 6 pink electrons because it's oxygen, right? So I've already drawn 2. So 6 minus 2 is 4. So I need 4 more. 1, 2, 3, 4. So that's 1 oxygen. And then the other oxygen on the other side does exactly the same thing because it also needs 2 electrons. So it's going to share 2 to have 2. Fair, fair, fair. And then adding that in. Now, after you draw dot and cross, you must always check that you have a full shell for everyone. So let's check the oxygen first. Oxygen, just look at the oxygen here. Does it have 8? 1, 2, 3, 4, 5, 6, 7, 8. Happy. Check the same for the right-hand side. Also 8 electrons, including the 2 purple ones from the carbon because it's sharing now, right? And then what about the carbon in the middle? Does it have 8? Yes, it does. And this is the dot and cross diagram for carbon dioxide. So use the periodic table to help you, and then also count the total electrons in the end to make sure you didn't miss anything out or you didn't draw too many. Sometimes some students, they do that. And you see that's a real problem because now oxygen no longer has 8, it's got 10, and that's wrong. So it helps to really count them and make sure you haven't drawn too many. Okay, part 2, it says, the atoms in carbon dioxide are held together by covalent bonds. Describe the forces of attraction in covalent bonds. So when we think forces of attraction, I want to think of positive and negative attracting each other. Otherwise, there wouldn't be any attraction. So the positive part, what's positive? Just stare at it and tell me what part of this is positive. What is a positive thing? The proton. Right? And where's the proton? That's in the nucleus. So where's the nucleus? It's going to be here and here and here. Agree? That's the positive part. So that is the nucleus. And since I have more than one nucleus, I'm going to say positive nuclei. This, guys, nuclei is an underlined word. The mark scheme I'm looking at right now says reject nucleus. You cannot write nucleus because there's 3 nuclei here. More than one is nuclei, not nucleus. Do not say nucleus. And then there's no point just having positive, right? Where's the attraction? I need the negative. What's the negative? Where's the negative stuff? I'm seeing lots of negative things. What is the negative stuff that's contributing to the bond between these three things here? It's the electrons here and the electrons here. It's not, guys, look, it's not these electrons on the outside. These electrons pay no contribution to the covalent bond because they're not even between the nuclei. Do you see that? So it's only these electrons, and these electrons are called shared, let's write negative first, negative shared pair of electrons. Negative shared pair of electrons. And then what about these two? You would say the electrostatic forces of attractions. Understand? So basically you would write the electrostatic force of attraction between the positive nuclei and the negative shared pair of electrons. This is the definition of a covalent bond. Please memorize it. Don't tell me that covalent bond is the bond between a metal and a non-metal. Between a non-metal and non-metal. That is not the official definition of a covalent bond. So this is the official definition of a covalent bond. Okay, great. This one, bonding. Bonding, very straightforward. This is not bonding, it's about conductivities. Explain why graphite conducts electricity. These are all carbons, different forms of carbons. I hope you guys know that these are allotropes of carbon. Allotropes means just different versions or how it's arranged differently. Allotropes of carbon. And explain why graphite over here conducts electricity. Now, when you think about conductivity, I want you to think of two things. Number one is mobile. Number two is charge. And you've got to tick both boxes in order for something to conduct. It's an and, not or, and. It's got to have mobile and charge. So what I mean by that is there a charge in graphite? Yes, those would be the electrons. Electrons are negative charges. Is there any mobility? Are the electrons moving? Can they move? And if you know your graphite structure, you know that it has a layer right here between, they've got three layers here that I've drawn out for you. And in between these layers are delocalized electrons, right? Right here. Doing here. That's where it is. So you would put this as delocalized electrons, right? It has delocalized electrons, which can move and therefore carry a current. It's got delocalized electrons. And you should mention that it can flow through the structure. Because if it cannot flow, then again, it cannot carry a current, right? So flow through the structure. And therefore, guys, if this question asks you why diamond cannot conduct, then you would say the exact opposite. You'd be like, there are no delocalized electrons. That's how you would explain conductivity. Okay, explain why diamond has a much higher melting point than C60 fullerene. Refer to the structure and bonding in your answer. Okay, so we're comparing diamond, this one, and the fullerene over there. Now, when you see diamond, you should put down a keyword which is that it is a giant covalent. And why would that give it a higher melting point? Because there are it's a giant structure, or sometimes we call it a lattice structure. So you would say that there are a lot of strong, there's strong covalent bonds, which requires a lot of heat energy to break, or thermal energy to break. And that's just part one of the question, 5 marks. You have to talk about the other one as well because you're comparing. So then what would you say about the fullerene? Same structure, right? I mean, the same way you would answer this question. Is it a giant covalent or is it a simple molecular? It's a simple molecular because there's only 2 giant covalents. It's either graphite or diamond. C60 does not have a giant structure at all. So it's a simple molecular structure. And therefore, what kind of bonds does it have? It doesn't have bonds. It doesn't have very strong bonds at all. It has weak intermolecular forces of attraction, molecular IMFs, right? Intermolecular forces of attraction. And then just mirror what you wrote up here. Then what did you say? You talked about the heat required to break, right? So now you would say does not require a lot of, or requires very little, right? Does not require a lot of heat energy to break these intermolecular forces. Do you see the parallels here? You've compared the structure. One is giant, one is simple. And then you've compared what bonds you're breaking. For the diamond, you're breaking the strong covalent bonds. For the fullerene, you're breaking the intermolecular forces, which are weak. And especially make sure you mention the strong and the weak. And then you talk about a lot of heat or not a lot of heat. That way you've covered every single point you need to get full marks on a bonding question. Remember, melting point questions, you must mention the amount of heat energy required. Don't just talk about the structure. Okay, question 11. This question is about the reduction of metal oxides. Solid oxides of copper can be reduced by reacting them with methane gas. Complete the equation for the reaction between copper oxide and methane. Include state symbols. Okay, let's put in the state symbols first. So copper oxide is a solid, you should know that, is a black solid. CH4 is a gas. It's methane, which is actually a greenhouse gas as well. So that's gas. Copper, what would you guess copper's state symbols to be? Solid, liquid, or gas? Copper, like a coin, literally a coin. So that would be solid. Carbon dioxide, obviously a gas, yes. And then water would be a liquid. Don't write aqueous for water because aqueous means it's got water added to it, and you can't add water to water, so it's just liquid. And then we're going to balance the equation. How are we going to do that? You can see that on the left side of the equation, I've got 4 hydrogens. On the right side of the equation, I've only got 2 hydrogens. So I'm going to balance it by adding a big 2 here, and therefore I have balanced the hydrogens. The next thing I'm going to tackle is let's check the carbons. On the right-hand side, I've got 1 carbon. On the left-hand side, I've got 1 carbon. So the carbons are happy. Now let's check the oxygen. On the right-hand side, I've got, how many oxygens have I got here? How many? Over here, how many oxygens? I've got 2 times O. So that's 2 oxygens, right? 2 oxygens here. And then over here, I've got 2 oxygens. So total on the right-hand side, I've got 4 hydrogens. And then on the left-hand side, I've only got, sorry, this is left-hand side. I've only got 1 oxygen. So 4 on the right, 1 on the left. I need to make them balance. So what do I write here? I write a big 4, a big 4. So now the oxygen is balanced, and then I've got to check the coppers now. Left-hand side, 4 coppers. Remember, 4 applies to everything here. 4 coppers. And right-hand side, only 1 copper, so I need to write a 4 right there. Yeah. And everything else is balanced, so I don't need to add any more carbons, and therefore I just write a 1 here and a 1 here. And you can check that. Okay. Then it says the teacher uses this as a operator to demonstrate the reaction between a different oxide of copper and methane. So this is an oxide of copper right here, and they're going to pump methane gas through here so that there's some sort of reaction. And it says the teacher heats the oxide of copper until the reaction is complete. The table shows the teacher's results. Use the teacher's results to show that the empirical formula of this oxide of copper is Cu2O. Right. So typical question on calculating empirical formula. For empirical formula, you're going to always write the elements at the top. So what are my elements here? it's an oxide of copper. So the only elements in there is copper and oxygen. Copper and oxygen. And then you're going to do your mass, Mr., mole, and ratio. So I just want you to remember this is how you do this sort of calculation. You memorize that. Mass, Mr., mole, ratio. And of course, Mr. is the mass number. That's the big number in the periodic table, the big number, the mass number. Then we just fill this in. So copper has a mass of, they didn't make it straightforward for you, the weighting boat plus the copper, so the boat required to carry it right here, this one here, that weighting boat plus the copper is 18.23, but without the copper, the boat itself is 15.05, and therefore the copper will be 18.23 minus 15.05. 18.23 minus 15.05, and that will be 3.18. Understand? Right? 3.18. So that is the mass of the copper. And what about the mass of the oxygen? Again, you have to work it out. Just look, what would you use to figure out the mass of the oxygen? This one is the copper plus boat. This one is the copper oxide plus boat. So if you just subtract these two, you would get the oxygen, right? Because the only difference between these two is the oxide. So oxygen is equals to 18.63 minus 18.23, which is 0.4. So oxygen is 0.4 grams. Then we find the Mr., the mass number in the periodic table, and if you look at it, copper should be 63.5 and oxygen should be 16. Then what is your equation for mole? Mole is equals to mass over molar mass. This is the only equation that you need to remember for chemistry IGCSE. So it's very important to know this. And I'll just basically divide this by this. So 3.18 divided by 3.18 divided by 63.5. 3.18 divided by 63.5. That would be 0.05. And then 0.4 divided by 16 will be 0.025. Then I need to find the ratio. The ratio means the simplest ratio. So you divide both numbers by the smaller number. The smaller number. So which one's a smaller number? 0.025. So I'm going to divide 0.025 by the small number, which is also 0.025. And I'm going to divide this one also by 0.025. And I should get 1 for this number and 2 for this number. 0.05 divided by 0.25, I should get 2. And that gives you the ratio. Because, guys, remember, empirical formula is the simplest ratio. So what is the simplest ratio? Have a look. Here it is. 2 coppers to 1 oxygen, which is exactly what is here, isn't it? The 2 coppers to 1 oxygen. So just by having this table, you've already proven that the equation would be Cu2O1. Cu2O. So that's how you do empirical formula. Okay, the teacher wears safety goggles and a lab coat during the demonstration. Give one other safety precaution that should be taken. Well, look at the diagram, right? It says excess methane burning. This is gas. Methane is any kind of gas is, you be quite careful because it could be toxic, and therefore you would use a safety screen because you don't want anything to you don't want to inhale a lot of that, right? Safety screen in a fume cupboard that will remove some of the gases. You don't end up inhaling it, and so on. Okay, great. Part C then. Iron forms when iron oxide is heated with carbon. The equation for the reaction is this. And I state how the equation shows that iron oxide is reduced. So, if anything that's oxidized will gain oxygen. That's a no-brainer, right? And anything is reduced, therefore, would do what? It will lose oxygen. So just have a look at who we have here. We have the Fe2O3, and then by the end, afterwards, it's turned into Fe. So would you agree that it's lost oxygen, isn't it? So that's literally what you write. You say that it has lost oxygen. Next part, state why carbon monoxide should not be released into the atmosphere. Poisonous, toxic. Why? Because it reduces oxygen transport. This is also tested in biology. So remember the harms of carbon monoxide gas. Right, finally, calculate the maximum mass in tons of iron that can be produced when 30 tons of iron oxide reacted with an excess of carbon. Okay. So, we need the equation right here. So Fe2O3 plus 3 carbons makes 2 Fe plus 3 CO. Okay? Now, we also need some information from the periodic table, because whenever you do calculations, you need to use the mole equation. Now, the way to do these type of equations is anything relating to amount of things that are produced. This kind of question that involves mole calculation, I want you to get in the habit of drawing this table. You're going to still have the mass, the Mr., which is the mass number, mole, and then the ratio. You're still going to have these four, same as the empirical formula calculation just now. And then at the top here, I want you to write what I need, actually what I know first of all, because they're going to give you some information that you know about. And then what I need to find out, what I need to calculate. So what you know is what they told you, and what information have they given you? They didn't give you information about all four of these things. They only gave you information on the iron oxide. Iron oxide, which is this one here, which is 30 tons. And therefore, the thing I know is iron oxide. Iron oxide. And I need it to be a mass, which has to be in grams, because that's the calculation for mole, right? Mass over molar mass. Mass has to be in grams. So if it is 30 over here, if it is 30 tons, then it's telling you here that 1 ton is 1 times 10 to the power of 6 grams, then 30 tons would just be 30 times 10 to the power of 6 grams, right? So that's my number here, 30 times 10 to the power of 6 grams, like that. And then the Mr., or the molar mass of iron oxide, which is this one here, right? That would be 2 of iron plus 1 of oxygen 3. And then you need to find that information in the periodic table and add it up. So 2 times iron plus 3 times oxygen, and that should be 160. And then you do your calculation for mole, which is just mass divided by 160, mass over molar mass. And that should give you 187,500. And then I don't do ratio yet. I can't do ratio because I need both information to work out the ratio, right? Look at this up here. Look at this. I needed both of these so I can divide by the smaller number to get the 2-to-1 ratio. So I don't need to worry about that right now. I'm going to move on to what I need to calculate. So what are they asking for? It says calculate the maximum mass in tons of iron. Iron. So that means this guy. All of these, ignore it. Useless information. So just the iron. So therefore, let's also color code that. That's what I need to calculate. And I'm going to put a question mark right here so that I know exactly what I'm trying to arrive at. It's asking for the mass, right? The mass in tons, by the way, in tons. Okay, so what information do I have that I can use to do this calculation? Do I have the Mr., the molar mass of iron? Yes, I certainly do, from the periodic table. Okay, so it should be 56. Iron should be 56. 56. And then what is the mole, guys? this is where the magical ratio comes in. The ratio refers to the mole ratio, which is the big number in front of your balanced equation. And in this case, the big number in front of the iron is 1, and in front of the iron oxide is 1, and in front of the iron is 2. So that's 1 to 2. See that? 1 to 2. So that's my mole ratio, 1 to 2. And the magical thing is, once you have this ratio, you can work out this number, because this is 1 to 2, just like 1 to 2. So in order to get this number, I just need to times this by 2, because that's how I get this number. I times 1 by 2 to get 2, right? So 187 times 187,500 times by 2, that would be 375,000. Understand that? So the mole ratio, well, the ratio is the mole ratio, which is these big numbers from your balanced equation. And then you use that to find out the number of moles, because the moles is the same as the ratio. Okay, so now that I've got mole and Mr., do you remember our equation? Mole is equals to mass over molar mass, right, Mr.? And since I'm trying to find the mass here, I better put that as the subject. So mass is equals to mole times molar mass. And the mole in this case is 375. Yes, so 375,000. And then the Mr. is for iron, because it's iron here, right? This is what I need, iron. So that's times by 56. 375,000 times by 56. Let me just do that. 375,000 times by 56. And that answer is 21 and a lot of zeros. 21, a lot of zeros. Okay, and therefore that would be my answer here. 21, 0, 0, 0, and then 0, 0, 0. And that's the answer I put in here, which is 21, 0, 0, 0, 0, 0, 0. Now, I specially did that to see if you spotted a mistake. Do you know what's wrong with what I've written? Just the last step. I've written this. What is the unit of this? This is the mass, right? I'm working out the mass. The unit for this equation is mass in grams. So therefore, this is in grams, guys. It's in grams. You better write that down so that it will show you what you've worked out. But the question doesn't want grams. It wants tons. It wants tons. So what I should write is here, this is in grams. But how do I turn that into tons? This is not right. I need to go backwards. So I just need to divide it by 1 times 10 to the power of 6. So I divide it by 1 times 10 to the power of 6. And that basically just gets rid of the 6 zeros if you calculate it on your calculator. And the answer is 21 instead of 21 million tons. Is that okay? And just use your brain to what I call a logic check. If you start off with 30 tons, does it make sense if you ended up with 21 million tons? No way, right? That's not very likely. Now, if you ended up with 21 tons, that sounds a lot more feasible. So just use your brain to see if your answer even makes sense. Okay, right. Last question. A mixture of 25,000 mole of iron oxide and 840,000 grams of carbon is heated. Use the equation to show that iron oxide is in excess. So, same thing. Mole calculation, what I write here? I write mass, Mr., mole, and ratio. And then, what are my superstars here? Which two am I focused on? What is what I need and what I know first, because you cannot get what you need without knowing something first. I need and I know, right? So what I know is in this case, you could choose either. But the main two things that are focused in this question is iron oxide and then the carbon. These two now. the last question was focused on the iron oxide and the iron, but this one is on the iron oxide and the carbon. That's why you need to know the two players. You get it? Right, so there's two things here, so let's put that in here. The Fe2O3 and then the carbon. Right, now, so for carbon, let's fill in what we know about carbon first. Is given here, 840,000 grams. So 840,000 grams. And what is the Mr. of carbon? Carbon is 12 from the periodic table. Guys, don't times 3. This is just to balance it, but the Mr. comes directly from the periodic table, which is 12. Carbon has a mass number of 12. So this is just 12. And then I'm going to calculate the moles, which is mass divided by Mr. So 840,000 divided by 12, and that's 70,000. So I would be getting 70,000 moles of carbon. Now, once you've worked out one of them, I want you to find out the ratio. What is the ratio of the yellow to the green? Remember I said ratio is a big number, right? So the big number here is 1, the big number is 3. So I'm going to write that down, 1 and 3. 1 and 3. And once I have the ratio, I can work out this number because these two numbers have the same ratio as these two numbers. So what that means is, if to get from 3 to 1, I divide by 3, right? So how to get from 70,000 to this number? I also divide by 3. So 70,000 divided by 3 is 23, and then 333. So 23,000, around 23,000. Around 20, let's write that in blue color, 23,333. Okay, now what is the Mr. of iron 2 oxide? The Mr. of iron 2 oxide from the previous question, you would have worked out as 160. You can check that if you need to, but it's 160. And then I'm going to go up and work out the mass. The mass is these two numbers multiplied together, which is 160 times by 23333. And the answer is 3, let me write this down, 3,733,280 grams. Okay, now what is the point of all this table? You're supposed to show them that iron oxide is in excess. So what do you notice about this table? Is that if we do the calculations like this, how many moles of iron oxide do I need? How many moles? If it was a perfect situation, I only need 23,000, right? Around 23,000 moles of iron oxide. But look at how much moles they actually had. They had 25,000 moles of iron oxide. So what does this tell you? Which one is in excess? Which one had too much? Iron oxide, right? Because you only needed 23,000 based on your mole calculation and all of that. But in reality, they used 25,000 moles, and that proves that iron oxide is in excess. So this is how you prove something is in excess or not. By drawing this table, mass, Mr. mole ratio, and then using the ratio to work out how many moles of each thing that you need. And then looking at the real situation and seeing, oh, did I have too much or too little? If the real thing is too much to what you calculated, that means you've used an excess of it. So that's how you've proven it. And that's it. Blue box is a mole calculation for the empirical formula. Make sure you remember, they won't give you this formula, the equation to calculate moles, which is mole equals the mass divided by molar mass. Then you draw a table with mass, molar mass, mole, and ratio. You fill in the numbers, you do the calculations, and then the ratio at the bottom will tell you the empirical formula. So in this case, the empirical formula is Cu2O1. In other words, Cu2O. Orange box is on organic chemistry. Make sure you know the different types of formula because they will ask you to write it or define it. So general formula is the CnH2n, which is for alkenes, and then CnH2n plus 2 for alkanes. The molecular formula is the actual number of carbons, hydrogens, or oxygens in your substance. The empirical formula is the simplest ratio of these atoms, and then the displayed formula is like this one below, where you draw out all the bonds so they can see everything. This example down here is a addition polymerization reaction of alkenes. Remember how to draw it, including the N here and the N at the bottom there. And you will have the double bond, but no more double bond here because it's opened up, is double bonds. Yellow box down here is on covalent bond. This is the dot and cross diagram of carbon dioxide. Make sure you check at the end of your drawing that each atom has 8 and 8 electrons to have a full shell. And then you also need to know the definition of a covalent bond, which is the electrostatic force of attraction between the positive nuclei and the negative shared pair of electrons. And then finally, purple box is on the allotropes of carbon, including diamond, graphite, and C60 fullerene. Now, you need to know two things about these three structures here. The first is the melting point. The second is the electrical conductivity. For melting point, diamond graphite has a very high melting point because it has strong covalent bonds, many strong covalent bonds that you need to break, which requires a lot of heat energy. Whereas C60 fullerene has weak intermolecular forces because it is a simple molecular structure and therefore does not require a lot of heat energy to break. In terms of conductivity, only graphite conducts because it has delocalized electrons.